Hey everybody, welcome to Chapter 4, Part 6, continuing our discussion of sensation and perception. This time we are talking about touch. Alright, let's talk about touch. This creepy looking thing over here is our sensory homunculus. It's basically what your body would look like if the size of your body parts was a function of how sensitive they are to touch, or if they occupied the same amount of physical space as spaces they occupy on your sensory cortex. So our sensitivity varies a lot by location. So your hands are really, really sensitive, your lips and face are very sensitive, your back is not very sensitive, right? We have a much lower density of receptors on our back than we do on our hands, and we have a much larger area of our sensory cortex, relatively speaking, dedicated to our hands than we do to our back. So sensitivity varies by location. So we really only have four sensations, touch sensations. We have pressure, warmth, cold, and pain. Combinations of these senses are what lead to other sensations, right? So you can feel when something is wet, but that's really just a combination of, for example, cold and pressure. If you've ever gotten something out of the laundry, maybe when it's cold out, and you're not sure if the thing you're holding is wet or if it's just cold, that's because pressure and cold feels a lot like wet. It's all just combinations of these basic sorts of inputs. So let's talk about the cutaneous senses, right? We have touch, which is accomplished by encapsulated receptors, which are mechanoreceptors, right? They respond to physical, mechanical stimulation. Movement of the skin results in movement of receptor dendrites, which are located within encapsulated endings. So we have these weird encapsulated receptors in our skin that when they're crushed or moved around or manipulated by movement of the skin, these dendrites are sensitive to that, and they can produce that signal of pressure. There's also temperature, right? We have two thermal receptor categories: cold sensors, which are located just below our epidermis, and warmth sensors, which are located more deeply in the skin. These respond to changes in temperature and also to the presence of certain chemicals. Pain is our third type. There are three types of pain receptors, or nociceptors. These respond to intense pressure, so striking, stretching, pinching of the skin will cause stimulation of some nociceptors. Others respond to extreme heat, acid, or capsaicin, so the agent that's in some spicy foods is actually triggering a pain response. And then there's also environmental irritants, inflammation-inducing chemicals, etc. So the combination of these receptor types that we've talked about, touch, temperature, and pain, allow you to experience the full experience of a hot pocket, right? The crumbly, weird outside, the scalding hot bit that you get with your first bite, and that will burn you and cause you pain, and the icy cold center that is still frozen. So let's talk a little bit about pain. Pain, like thermoception, is accomplished by free nerve endings in your skin. High threshold mechanoreceptors will respond to intense pressure, striking, stretching, or pinching, and some free nerve endings can respond to extreme heat, acids, or chemicals such as capsaicin. Some respond, as I mentioned, to environmental irritants such as inflammation-inducing chemicals. So why is pain important? Well, it's evolutionarily adaptive, right? Nobody likes having pain. It's very unpleasant, but it protects us from repeatedly damaging our bodies. If you hurt yourself doing something, you learn very quickly that you shouldn't do that, or at the very least, you should be more careful. There exist a number of disorders that cause insensitivity to pain. For example, congenital insensitivity to pain with anhidrosis, or CEPA. I can post a video of a patient with this. This causes an inability to feel pain, heat, or cold, but they can still feel normal touch pressure. People with this disorder don't do very well. Oftentimes, since this is congenital, people are born with it. And if you've been around children, you know how reckless they can be. Without pain as a teaching signal, kids can end up really hurting themselves. They can damage their eyes by touching them and not feeling any pain. They can bite through their tongues. They can exert tremendous pressure on their joints because they don't feel that they're pushing them too hard. They can cut or otherwise hurt themselves and not really make a connection between the pain and what's caused it because they don't feel that pain. While it sounds nice and almost like a superpower to be immune to pain, it makes surviving really, really difficult. So I want to talk very briefly about phantom limb pain. Phantom limb pain is the sensation that an amputated limb is still attached to the body, and this is very commonly experienced in people who have had to undergo an amputation. Patients might report feelings of pain, pressure, tickling, temperature, etc., typically very unpleasant. It's usually painful or at the very least uncomfortable. The neurological basis of this is still debated. This could be due to cortical reorganization, loss of a limb that results in adjacent regions moving into that territory, and that sort of reallocation of neural resources might cause some confusion and misfiring, leading to the perception of a limb that's no longer there. Likewise, this could be due to the peripheral nervous system and proper inputs at nerve endings near the site of amputation. So they're used to receiving some sort of an input, and now they're receiving weird different inputs, and that improper input in the periphery could give rise to the perception of a limb that's no longer there. I'll post a video about a case study with an individual who is suffering from phantom limb pain, and a really, really unusual technique called mirror therapy, which sort of tricks your perception into believing that a limb is still there, and it can cause a surprising amount of relief from phantom limb pain. So I'll post a video about that also under perusal. I want to mention the kinesthetic sense. This is a type of touch sense that we don't think about very often, but is extremely important. Right? So this allows us to have a sense of the location and position of our body parts in relation to one another. So proprioceptors are sensory receptors located in muscles and joints that provide information about body position and movement. So this isn't something you think about often, but it's really, really important, right? I can close my eyes and I can pick up this mug that's next to me and I know where it is and I can move it around. I'm not looking at it, but I can tell where my limbs are in space and where this thing is that I'm moving around, right? Without that, you can imagine it would be really, really hard to look around. People who have lost their proprioceptive abilities, for example, can't walk without looking at their legs. They lose track of where their body parts are because they can't feel where they are. This is one of those really basic senses that we take for granted, but would just be super weird to live without. Speaking of weird senses that we take for granted, the vestibular sense. This allows us to sense the position and movement of the head and body that enables us to maintain balance. We have these fluid-filled chambers with hair cells that work somewhat similarly to the hair cells within our ears that send messages about head position and orientation. These are called vestibular sacs and semicircular canals. So you can see here vestibular sacs are these sort of oblong things, and semicircular canals are what they look like. They are semicircular canals. These contain a sort of fluid with these little bits of debris inside, little chunks of calcium carbonate that sort of move along with the fluid. And you've got these hair cells in there that are sensitive to being knocked around, more or less. So when you move your head one way or the other, it causes the fluid to sort of swirl in the opposite direction that you're moving. And as this fluid sort of moves across those hair cells, it displaces them. And that mechanical reception causes transduction to take place, and you get the sensation of your head moving around. It's one of the reasons why if you spin around really fast and then stop, you become dizzy. Because you have this weird, stupid, slow system in your brain where you have this fluid moving across hair cells, and when you stop, fluid doesn't stop right away. Fluid keeps spinning because you've been moving pretty fast. And as that fluid continues to move across those hair cells, you get the continued perception of motion, right? So you get this weird conflicting sense of your vestibular system saying, hey, we're still moving, we're spinning around in a circle. But your muscles and your eyes say, no, we're not, we're standing still. So you get this weird conflicting input of we're spinning, but no, we're not, which makes you feel dizzy. Okay, that's it for vestibular sense, and it actually concludes the portion of this chapter where we're talking about sensation. Next, we're moving on to a discussion of our perceptual process.